Welcome to the PowerPoint on electrolytes. So this is going to be kind of a tag along with the kidneys PowerPoint, and this really focuses on the salts, sodium, potassium, and chloride. So we're going to get started just talking about the term balance. So the kidneys function is really to balance water, electrolytes, and acid base. Balancing water determines blood pressure and blood volume. So average daily water intake and loss should be about equal. And then electrolyte balance, this is going to be balancing that sodium, chloride, and potassium between the blood and the urine. And then the last one is acid-base balance. And as you know, the concentrations of protons that you have will determine your acidity. So acid-base balance is controlled partially by the kidneys, and it's dependent upon how much you rid your blood of protons. And of course, all of these must be balanced. You're not trying to just get rid of all electrolytes and acids in your body. It needs to be balanced between the urine and the blood. So how do we understand? How does our body essentially understand or see the amount of solute that you have and the concentration of the blood and plasma? Well, it's through a type of receptor called an osmoreceptor. This type of receptor is a receptor for osmolarity, the concentration of solutes within the blood plasma. And this kind of receptor is going to be found within your hypothalamus, which, as you remember from anatomy, is in the brain. The osmoreceptors respond to angiotensin II. Now, if we go back to the last PowerPoint, we learned about the renin-angiotensin system, and you learned that angiotensin II was the active form of the enzyme, and this caused a few different things to occur in your body. You secreted it when your blood pressure dropped, and with that, you were able to trigger thirst, you were able to trigger vasoconstriction, and you were able to trigger secretion of aldosterone. Osmoreceptors have the ability to communicate with the hypothalamus and the cortex, and the hypothalamus itself is special because it makes the hormone called ADH. We haven't gotten to endocrine system yet, I don't think, so when we do, we'll learn more about this, but for now, I just need you to know that the hypothalamus itself produces antidiuretic hormone. You learned about this one in the kidneys section as well, and ADH promotes water conservation. So this helps your body hold in water. Now, before I move on, let me go over a few terms in a very elementary way. The term osmolarity means the measure of concentration. So you're measuring how much salt versus water you have. When osmolarity goes up, that means you have a higher concentration of salt in that solution. So osmoreceptors measure the osmolarity of your blood. Now, if the osmolarity of your blood rises, that means you have a higher salt to water ratio. And sometimes that osmolarity can go too high. Let's say you ate something really salty. You had maybe 3 cup of noodle soups in one day, and your sodium levels are just off the charts. The osmoreceptors are going to sense that, hey, this person's osmolarity is very high. We have a very high salt to water ratio. What are we going to do? Well, to bring this ratio down, you can either get rid of salt or you can just increase the amount of water that you have. This third bullet point states that the hypothalamus produces ADH, a hormone that produces water conservation. This means that you're holding water in. So this pathway right here essentially increases the water volume to decrease the osmolarity. You're also going to signal the cerebral cortex to trigger thirst. So you're going to say, hey, drink some water. So not only are your kidneys holding in water, but now you're going to be drinking water for yourself. Salivation is also inhibited at this point because your body's trying to conserve that fluid. So let's look at a pathway. This pathway and the next one are similar but not identical, so I'm going to go through them one by one. Let's say you're out on a hot day. Maybe you're gardening, maybe you're stranded on a desert island like this picture, and you get dehydrated. The word dehydration means that you're losing what? What are you losing in dehydration? In dehydration, you're losing water. So when you're dehydrated, you lose water out of your body. What that means is your osmolarity is going to increase. But because you lost the water, Although your osmolarity increased, your blood volume decreased because you lost that water volume. And if you lose blood volume, you also lose blood pressure. So let's go through this part first, since this is truly the review for us. Reduce in blood pressure will cause you to secrete renin. Renin activates the angiotensin pathway. You eventually make angiotensin 2, and angiotensin 2 will stimulate the osmoreceptors. So, osmoreceptors have the ability to reduce salivation, to increase the sense of thirst as well, to increase how much water you have ingested. So, we're going to stop here for the right side. Let me go to the left side really quick. Dehydration, again, causes you to lose water, and therefore it increases your blood osmolarity, so you have a higher concentration of blood. And because you increase your osmolarity, this is also another trigger for osmoreceptors. So you've learned now 2 triggers for osmoreceptors. You've got angiotensin 2 and an increased blood osmolarity. Both situations lead you to the same output of the same reactions, reducing salivation, creating a sense of thirst. So eventually you ingest water. That's going to moisten your mouth, so you will have nice saliva again. It'll rehydrate your body, and it causes your stomach to distend. That means to stretch out. This will cause a short-term inhibition of thirst, and then you can go ahead and cross off this long-term inhibition of thirst. I've taken it out for you. Now, going into the physiology of how all this works, and this will be a little bit of overlap between the last slide. Again, let's say we start off with dehydration. Dehydration means you are low in water, but you are high in salt. Because of this, it causes an increased blood osmolarity. High osmolarity triggers osmoreceptors. Osmoreceptors is going to cause release of ADH from that pituitary gland. And then once you secrete ADH, ADH has 2 main effects. ADH is going to stimulate thirst, and it's also going to stimulate the distal convoluted tubule, the DCT, and collecting duct. And if you wouldn't mind, just make sure that you understand that these 2 are part of the nephron, and that ADH, when it signals these 2 regions of the nephron, it's going to increase water reabsorption. So it's going to cause water to move from the tubule back into the capillary bed next to that nephron. Eventually, you will have a reduced urine volume because, again, you're moving that fluid from the tubule back into the blood. And you're going to have an increased ratio of sodium to water in the urine. So not only do you reduce the volume of the urine, but you're increasing the concentration of the urine. So with those physiological pathways, the real big goal here is to balance electrolytes. So that's what this PowerPoint is on, electrolyte balance. The major ones we're going to look at are sodium, potassium, calcium, and hydrogen. And then the major anions we're looking at is chloride, bicarbonate, and phosphate. Don't forget that bicarbonate is a buffer, and we learned about this in the respiratory system lecture. So with that being said, we're going to start with sodium. Sodium is the main ion responsible for your cell's resting membrane potential. So if you recall, the cell's resting voltage, or that resting potential, was around negative 70 millivolts. And that's because you had a high sodium concentration on the outside relative to the inside of the cell. So sodium is about 90 to 95% of the osmolarity of your extracellular fluid. This is the most significant ion that you have that really does control all of your water balance, and therefore your blood pressure. Sodium gradients are also sources of potential energy for cotransport. If you remember the sodium glucose symporter, any of the symporters that use sodium's downward gradient to get into the cell to piggyback with it, that's what we're talking about here. So maintaining a high sodium concentration outside the cell is very important. And the way to do that is with the sodium-potassium pump. This pump forces sodium out while forcing potassium in. And then we have sodium bicarbonate. We don't actually ever call it sodium bicarbonate when we're teaching you the physio lessons. We just call it bicarbonate by itself because we're talking about the ionized form. But the molecular form is sodium bicarbonate. When this goes into solution, It ionizes into sodium plus ions and bicarbonate minus ions. Both of these stay in the extracellular fluid. So, how do we control sodium concentrations? Well, this should be a little bit of a review for you. Aldosterone, you learned about this in the kidneys PowerPoint. Aldosterone is a hormone that causes reabsorption of salt in the kidneys. So when you make aldosterone, aldosterone tells the kidneys to reabsorb more sodium. And wherever sodium goes, where else are you going to have water going? Well, water is going to follow that sodium concentration, and it's going to be reabsorbed along with it. Hyponatremia and hyperkalemia, these two terms, I'd like you to know the definitions of. Hypo, if you ever see the prefix hypo, that means low. Hyper means high. Natremia, it starts with an Na, so it's always for sodium. Kalemia starts with a K, so it's always for potassium. Hyponatremia, low sodium, and hyperkalemia, high potassium levels. Both of these will stimulate secretion of aldosterone. Make sure to know that these two are the stimulus for aldosterone secretion. Then you have hypotension, low blood pressure or low pressure of blood in the blood vessels. This is also going to secrete production of aldosterone. And the whole key behind this is, hey, if you have low blood pressure, why don't we make aldosterone to reabsorb sodium and therefore reabsorb water, bringing blood volume back up, causing blood pressure to also rise back up to normal. Not only does hypotension stimulate aldosterone production, but it does it by triggering the renin-angiotensin-aldosterone system. Again, this system is very important. We've now talked about it at least 4 or 5 times in 2 different lectures. Low blood pressure causes production of renin. Renin causes conversion of angiotensinogen into angiotensin 1. Angiotensin 1 turns into angiotensin 2, and angiotensin 2 is going to do a few different things in your body, one of which is stimulating aldosterone. Now, the primary effect of aldosterone, again, is to reabsorb salt from your urine and therefore water. And this is going to cause the urine volume to go down. Why? Well, if you're reabsorbing all the water, you're not going to let that water be excreted out. So, 2 more hormones that are going to help us control salt, specifically sodium concentrations. One is ADH, the antidiuretic hormone. And antidiuretic hormone is going to be stimulated by high sodium concentrations in the blood. Whenever you have too much sodium in the blood, that's also going to trigger hormone release. But in this situation, you're not trying to keep the sodium in the blood. That high sodium is going to stimulate your brain to release ADH. ADH is antidiuretic hormone. If the blood has a lot of sodium in it, one of the ways that we can correct this shift in osmolarity is by secreting ADH to reabsorb more water, allowing more water to stay in your blood, and therefore decreasing the overall osmolarity of your blood. The last one is ANP. ANP is atrial natriuretic peptide. This is secreted by the heart when your blood pressure is too high, and ANP is able to inhibit both sodium and water reabsorption. In essence, ANP causes elimination or secretion of both sodium and water in order to lower your blood pressure. The triggering factor for ANP is high blood pressure. So when your blood pressure is high, it stretches out the heart and it increases the pressure in the aorta. And you have baroreceptors in there that say, hey, blood pressure is a little bit high. Let's go ahead and secrete ANP so we can excrete out sodium and therefore water out into the urine. and get rid of that fluid from inside our body to lower blood volume and therefore lower blood pressure. So here are the terms that I'd like you to know: hyponatremia and hypernatremia, simply meaning too much sodium and too little sodium. Below them, it gives you potential ways in which you can cause too high or too low sodium. Please go ahead and read those, but no need to memorize these numbers. Moving on to potassium. Potassium is K+. This is the most abundant cation in the intracellular fluid. So remember, sodium on the outside of a cell, potassium on the inside of a cell. And because this ion is in the highest concentration, this is going to determine the internal osmolarity of the cell and therefore determines how much water goes into the cell, determining cell volume. So the potassium inside the cell also contributes to determining the resting membrane potential, as well as helping with action potentials of those muscle and nerve cells, as you already know. Now, if sodium is out of balance, that's not a very big deal. That can be corrected pretty easily. However, if potassium intracellularly is out of balance, that can be pretty dangerous. Why? Well, let's look at two potential situations. Hyperkalemia. This is going to be high potassium levels. This potential situation is going to be determined by how quickly that potassium level goes up. If the potassium level rises up very, very quickly, that can cause nerve and muscle cells to start getting excited very easily. That can start contractions or nerve impulses that should not have otherwise been sent. Hypokalemia means low potassium concentrations. This is usually not from your diet or not having enough potassium in the diet. This is usually from sweating too much, from diarrhea, or from chronic vomiting. So here's the example. If I go back one slide, here's the example of hyperkalemia and having that potassium rise too quickly. So we have our normal cell. Here's the normal concentration of potassium inside the cell, and we're at our normal resting membrane potential at around -60. The top cell is the situation with hyperkalemia. You can clearly see that the inside of the cell has about double the amount of potassium as does the normal cell. By increasing the intracellular potassium levels, you're increasing the voltage of the cell. Why? Well, potassium has a positive charge. The more of it you have in the cell, the higher your voltage is going to go. And the higher the voltage goes, what do you get closer to reaching? And I'll kind of draw a line here. That line is your threshold. Once the voltage reaches the threshold, if you recall, it shoots up an action potential, comes back down. This happens in muscles and nervous tissue. So if you have a higher membrane potential, you're closer to threshold, which means your cell is more excitable. The hypokalemia means you have too few potassium. So your membrane voltage is going to go lower. If your threshold is still up here, you're now further away from threshold. It's going to take you a much longer time to reach that threshold before shooting off the action potential. So we say that this cell is less excitable. These levels can adjust. Again, if you're sweating too much, you can be hypokalemic. If you're vomiting, you can be hypokalemic. And if you have diarrhea, you can be hypokalemic. All of those situations will deplete your cells of potassium. Hyperkalemia can be caused by some medications. It can be caused by kidney failure. So if the kidneys fail to excrete out high potassium amounts, and it can be caused by congestive heart failure as well. So the last ion we have is going to be chloride. This is the last of the three major ions, and chloride is the most abundant anion in the extracellular fluid. So the most abundant cation was sodium, and the most abundant anion is chloride. Chloride is required for some pretty important functions in your body, And one of them is going to be in your digestive system for production of hydrochloric acid. The chloride for HCl in your stomach comes from your blood. So not just that, but HCl is also made up of a proton. Chlorides are responsible for regulating pH by being able to bind and sequester free-floating protons. They also have a strong attraction to sodium, potassium, and calcium because of their opposing charges. And the primary homeostasis is achieved as an effect of sodium homeostasis. This means that wherever sodium goes, chloride is going to follow. So you could think of it as sodium being like the main leader, and wherever sodium goes, chloride follows, and also water follows. So you've got a nice system here where by controlling salt concentrations, you're also able to control water volume. Now, of course, these have their own terms as well. Hyperchloremia means too much chloride, and this is usually caused by IV saline administration. And then hypochloremia, it's usually a side effect of hyponatremia. So if you remember what this term means, it means too little sodium. This is usually because you're excreting the sodium. And if you excrete the sodium, who else is going to follow? Well, the chloride's going to follow. And again, if you excrete the sodium, who else follows? Water. So hypochloremia will also usually indicate low sodium concentrations as well as low water volume in the blood. And that's going to be the end of your electrolyte balance. This tags on to the end of the kidneys PowerPoint. So be sure to email me or text me if you guys have any questions, and I will make time for every single one of you. Hope you're all doing well, and I will talk to you soon. Bye.